Guys, so today I'm going to be covering the higher level content of the topic of inheritance as part of the IB biology curriculum. So essentially what we need to know for higher level is how two traits are inherited from parent to offspring, So this leads me to unlinked versus linked genes. Unlinked genes are when the traits or the genes for the two traits are found on two different chromosomes. So maybe one trait is found on this chromosome over here, and then another trait is found over here, and they are inherited separately. Whereas linked genes are when the traits are inherited on the exact same chromosome, and they are inherited together, not separately. So let's look at unlinked genes. Unlinked genes, in my opinion, are a little bit easier because we can utilize Mendel's ratio from standard level because they are inherited separately. So the example that the IB gave is peas, and the two traits that we look at is the shape of the pea, so whether they're round is the dominant, and if they're wrinkly, that's the recessive. And then also the color, so green is the dominant and yellow is the recessive. Now, because these genes are inherited separately, the offspring could inherit any of these genes as a combination. So when we are putting it down on a dihybrid cross, which is what we need for figuring out two traits, how two traits are inherited, we would need to find a combination for any of these that they could inherit. So they could inherit round and green, round and yellow, wrinkly and green, wrinkly and yellow. And then let's say that this is crossed with another pea that is also heterozygous for both traits. And then we do the same on the same side because you would have the exact same combinations for the second parent. And then we can fill this out as a Punnett, as you would a Punnett square. So this is what it looks like filled out. And the reason I chose two parents with heterozygous genes is because when you have this combination, it will always give you a ratio of 9 to 3 to 3 to 1. So if both parents are heterozygous, the offspring will always have a 9 to 3 to 3 to 1 ratio. And there is another ratio that you can also figure out based on what the parent's genotype is. So let's take the same P example, and let's say you have one heterozygous parent, but then you have one recessive homozygous parent. Now, the reason that this time there's only one line or a 4x1 grid is because this parent will only be able, the offspring will only be able to inherit wrinkly and yellow from this parent. So there's no need to fill out a 4x4 grid because it can only inherit one combination from that parent. So it would only be wrinkly and yellow. For this parent, it would be the exact same as before. And then we just fill it out. As you can see, it's a 1 to 1 to 1 to 1 ratio. And this will always, just the same way that the heterozygous parents will give a 9 to 3 to 3 to 1 ratio, a heterozygous and a recessive homozygous parent will always give a 1 to 1 to 1 to 1 ratio. So now we can move on to linked genes. And in my opinion, linked genes are a little bit more complicated than unlinked genes. So let's take an example for linked genes, which are hair and eye color. So hair and eye color are inherited together. And let's say that this gene this gene deals with hair color, and this gene deals with eye color. Let's say that brown is dominant and blonde is recessive, and then brown is dominant for eye color as well, and blue is recessive. Let's say this person is heterozygous for both traits. So they've got brown hair and also brown eyes. But then we cross them over with someone who is recessive homozygous for both traits as well. Now the offspring can only inherit one of these chromosomes from each parent. So they can only inherit from this parent brown hair, brown eyes, or blonde hair, blue eyes. And from this parent, they can only inherit blonde hair and blue eyes. And so we fill this out, and in the end, we are left with a phenotypic ratio of 1:1. So this child can either have brown hair and brown eyes or blonde hair and blue eyes. Now, this phenotypic ratio can change a little bit through the process of recombination. And recombination is essentially the process of two homologous chromosomes pairing up, and then part of their DNA are switched. So let's say that we have the heterozygous parent, and let's say that this part of the DNA is swapped out, so there's crossing over here. Now we have a different combination of genes that this child can inherit. So whereas before it couldn't inherit blonde hair and brown eyes, it now can, and now it can also inherit brown eyes and brown hair, and blue eyes. So now it adds two more combinations that this child can inherit, and this is called a recombinant, as in the chromosome is called a recombinant. Now this doesn't always work. So for example, if the genes were found, the gene for hair was found really close to the genes for eyes, and then this part over here was crossed over, you would still have the same combination of genes. So it doesn't matter that a recombination happened, but in our case, let's say that the recombination happened where the genes are found. Now what happens is that the recessive homozygous person, obviously they can only, again, give the trait of blonde hair, blue eyes, but the heterozygous person can give the original brown hair, brown eyes, or blonde hair, blue eyes, but it can now, I did not give myself enough space, but it can now also give blonde hair, brown eyes, or brown hair, blue eyes. So now we fill this all out, and in the end we get this. However, this does not mean that it's a 1:1:1:1 ratio. It is a 1:1 to 0.1 to 0.1 ratio, and that's again because recombination may not happen, or recombination happens and it doesn't target this specific gene, therefore the recombination of that gene doesn't happen. So yeah, that's all for higher level inheritance. I hope this was helpful, and again, as always, I will leave the whiteboard down below.